Hi everyone, today's topic is to derive an expression for carrier concentration of N-type extrinsic semiconductor. Here concentration of charge carriers in N-type semiconductor. Before that, how these N-type extrinsic semiconductors are formed. Here we are going to consider an intrinsic semiconductor like silicon. It is a tetravalent atom. It is doped with a pentavalent impurity like phosphorus. Pentavalent in the sense 5 valence electrons. So among the 5, 4 valence electrons of phosphorus will be covalently bonded with the strong bonding between the two. With the silicon, all the 4 silicon valence electrons, thereby 1 electron of the phosphorus will be acting as donors, that is a negatively charged electron, make this semiconductor as N-type semiconductor. N-type denotes negative type, where the majority charge carriers are electrons and the minority charge carriers are holes. So here in this part, the explanation for the diagram drawn here is, we have a valence band here and a conduction band. At 0 Kelvin temperature, the N-type semiconductor, the conduction band is empty. All these donors, they form an energy level called donor energy level. ED denotes donor energy level, and we know already that EV is the highest energy level of the valence band and EC is the lowest energy level of the conduction band. And these donors, they form an energy level called donor energy level. Based on the dopants, we have donor energy levels. In the N-type semiconductor, the donor energy level will be positioned near to the conduction band, and the position of Fermi energy level in the N-type semiconductor will be between EC and ED. When the temperature of the semiconductor is increased above 0 Kelvin, then the donors at the donor energy level, they will be moving to the conduction band. Based on the temperature, the movement of electrons, donors, will be from the donor energy level to the conduction band. So we are going to derive how many number of electrons are present in the conduction band per unit volume of the N-type semiconductor. So from the diagram, we can see that there are 4 electrons present in the conduction band of N-type semiconductor. Here in the donor energy level, there are 4 holes present. Therefore, we can say that number of electrons in the conduction band is equal to number of holes at the donor energy level. So this is the base point. So in N-type semiconductor, we are going to find the carrier concentration, charge carriers concentration. Concentration of charge carriers in the sense how many number of electrons are present per unit volume of this N-type semiconductor. Now, in an intrinsic semiconductor, the number of electrons in the conduction band can be determined using this formula, 2 into 2 pi me kBT by h square, the whole power 3 by 2 e power ef minus ec by kBT. Here why intrinsic semiconductor carrier concentration has been taken. Number of electrons in the conduction band of intrinsic semiconductor is considered. For this, the explanation is the difference in the energy band structure of intrinsic and extrinsic is the position of Fermi energy level based on the dopants. So here in the intrinsic semiconductor, we have valence band, valence electrons are present here, and the Fermi energy level will be exactly in the middle at 0 Kelvin. In extrinsic semiconductor, say in n-type semiconductor, we have conduction band here and here valence band. Based on the dopants, donor energy level will be formed, thereby the Fermi energy level will be positioned between the conduction band and this donor energy level. So the position of Fermi energy level should be determined for n-type semiconductor, and then it has to be substituted in this formula, thereby we can find the carrier concentration of n-type semiconductor. So here the position of Fermi energy level has to be derived. So as per the diagram, number of electrons in the conduction band of n-type is equal to number of holes at the donor energy level. So we know the formula, the general formula for number of charge carriers or number of electrons is, that is Z of E dE F of E. This is the general formula as far as metals are concerned, because metals have only one type of charge carrier. Metals are rich in electrons, therefore electrons are the only charge carriers there. Here we are going to derive this expression based on this particular criteria. Number of electrons in the conduction band is equal to number of holes at the donor energy level. Therefore, we are going to find number of holes at the donor energy level. Number of holes at the donor energy level. So for this, the formula is NH is equal to number of donors, donor energy level, donors 1 minus F of E. We know that F of E is the Fermi distribution function or the probability function to find the distribution of electrons or electrons occupancy at a particular energy level, whereas 1 minus F of E denotes the holes distribution or holes occupancy in the energy level. So NH denotes number of holes at the donor energy level, so which can be determined as ND 1 minus F of E. Here this particular energy level is donor. So substituting ND 1 minus 1 divided by Fermi distribution function has the formula 1 by 1 plus e power E minus EF by KBT is the formula. Here the particular energy level whose occupancy is being considered is the donor energy level. Therefore this E should be replaced with ED. Then taking LCM, we have ND and this 1 plus e power ED minus EF by KBT. That is, this LCM should be written minus 1 the whole divided by 1 plus e power ED minus EF by KBT. This 1 and 1 get cancelled off, and now ED minus EF, look at the diagram, ED minus EF. So since ED minus EF is negative, look at this, EF is at the higher energy level, ED is at the lower energy level. Therefore, ED minus EF. So, since ED minus EF is negative, that is very much lesser than KBT, this exponential value can be neglected, or we can write it as 1 plus e power ED minus EF by KBT is approximately equal to 1. This is because ED minus EF value is very much lesser than KBT. Therefore, we are going to neglect this. Number of holes at the donor energy level is equal to ND into e power ED minus EF by KBT. So this is the formula. Now we have a formula here for intrinsic, the number of electrons in the conduction band of intrinsic. We are here to find the position of Fermi energy level. Here, this particular portion, I am going to consider it as NC, some constant value here. Throughout, for simplicity, I am writing it in this way. So, number of electrons in the conduction band of intrinsic semiconductor is NC e power EF minus EC by KBT. Let this be equation number 1 and this as equation number 2, because the first equation we have rewritten as NC replacing these two terms. So under thermal equilibrium condition, we told that number of electrons in the conduction band of the n-type semiconductor is equal to number of holes at the donor energy level. The only difference between intrinsic and extrinsic energy level structure is the position of Fermi energy level. So if we find an expression for Fermi energy level, then easily we can substitute that in this formula and then we can find the number of electrons in the conduction band of n-type semiconductor. So equation 1 is equal to equation 2. I repeat it. I am going to derive expression for carrier concentration of n-type semiconductor. For this, number of electrons in the conduction band is equated with how many number of holes are present at the donor energy level. For this, intrinsic is taken. The position of Fermi energy level has to be determined and to be substituted in the formula of intrinsic. Then we can determine the carrier concentration of n-type. So equation 1 is NC e power EF minus EC by KBT. Equation 2 is ND e power, I'm going to see the equation here, ED minus EF by KBT. Now mathematically we are going to derive this. This is taken to the denominator. Similarly, this is taken to the denominator of left hand side. So e power EF minus EC by KBT divided by e power ED minus EF by KBT, which is equal to ND divided by NC. Now solving this, it is just like e power m divided by e power n. I am going to write it as e power m minus n. So e power EF minus EC, and then here this has to be taken to the power minus ED plus EF divided by the same denominator KBT, which is equal to ND divided by NC. Here we have EF and EF, therefore e power 2EF minus of, I'm going to take these two as within bracket EC plus ED by KBT, which is equal to ND divided by NC. Now we need to find the position of Fermi energy level. Therefore here it is in the exponential power. Therefore taking log on both the sides, we get log E 2EF minus EC plus ED by KBT, which is equal to log of ND divided by NC, the base E. Log E to the base E is 1. Therefore we get 2EF minus EC plus ED. This KBT is taken towards RHS. We get KBT log ND divided by NC. Now this EC plus ED term is taken to the right hand side. We get 2EF is equal to EC plus ED plus KBT logarithm of ND divided by NC. Then this 2 is also taken towards the other side. Therefore EF is equal to EC plus ED by 2 plus KBT by 2 logarithm of ND divided by NC. So let this be equation number 3. So we have found the position of Fermi energy level in the N-type extrinsic semiconductor. We are going to substitute this formula or expression of EF from equation 3 in equation 1. So then we can find what is the carrier concentration of N-type. Therefore number of electrons in the conduction band of intrinsic semiconductor is Nc e power EF minus EC by KBT. This is equation number 1. So in this EF I am going to substitute equation 3. Therefore Nc, I am going to write the exponential and then with the bracket. EF is equation 3. EC plus ED by 2 plus KBT by 2 ln ND divided by NC. This is EF. Then we have minus EC by KBT. Therefore minus EC the whole divided by KBT. So what I have written here is this term is full of EF. This is EF. Now I am going to take LCM here. Here we have 2, here we have only 1. Therefore taking LCM, NC EXP is EC plus ED plus KBT log ND divided by NC minus 2 EC then the whole divided by 2 kBt. So we have taken LCM here. So here we have 1 plus EC, here we have minus 2 EC. So 1 minus EC I have. So this can be rewritten as NC EXP ED minus EC. ED minus EC. Here this 2 kBt is common for both these cases. So I am writing it in the form of ED minus EC divided by 2 kBt plus kBt by 2 kBt log of ND divided by NC. Then this kBt get cancelled off. This 1 by 2 is taken to the power of ND by NC. Therefore, NC EXP, that is, I am writing this again as ED minus EC by 2 kBt plus log ND divided by NC the whole power half. So this is just like e power, that is EXP m plus n. So we are going to write this as e power m into e power n. So we have NC e power ED minus EC by 2 kBt plus e power log of ND divided by NC whole power half. That should be into sign here, sorry, multiplication sign here. E log get cancelled off and ED minus EC is, look at the diagram, ED minus EC. From ED, donor energy level, the electrons are moving to the conduction band. So the energy required for the donor electrons to move to the conduction band is called as donor ionization energy, ED to EC. From ED, the electrons are moving to EC. So this is called minus del E, because EC is at the higher energy level, ED is at the lower energy level. Therefore, EC minus ED is del E, whereas ED minus EC is minus del E. Therefore, this donor ionization energy has to be taken here. NC e power minus del E by 2 kBt ND power half divided by NC power half. So here this NC power half is cancelled with NC power half and NC power half. That is, I am writing NC as square root of NC and square root of NC. So one get cancelled off and the remaining is written as NC power half, or even I can write it as root also. And then here I have ND power half. ND power half root, I am writing it as e power minus del E by 2 kBt. So number of electrons in the conduction band of N type depends on ND, NC e power minus del E by 2 kBt, but NC we need to expand here. What is NC? NC is, since NC is 2 into 2 pi me kBt by h square, the whole power 3 by 2. Then we have square root here. Square root in the sense power half. Therefore, power half and then power half should be written here. So we have 2 power half is root 2 and 3 by 2 into 1 by 2 is 3 by 4. Therefore, we have NC power half can be replaced with this term. Therefore, number of electrons in the conduction band of N-type semiconductor can be expressed as, that is NC is to be replaced here as root 2 pi me kBt by h square the whole power 3 by 4. This is for NC. And then we have root of ND. So I am writing it along with the 2. Then e power minus del E divided by 2 kBt. So this is the equation to find the number of electrons in the conduction band of N-type semiconductor.